same drawing. So again, Dijkstra's algorithm finds like the shortest distance from any vertex to another, but the algorithm will be like you pick kind of like, think of it as your root, and then it's going to find the distance to every other vertex from there. So if you care about the distance, say, from C to G, then you have to pick C or D as your root. Well, actually, because it's a directed graph, you need to pick C as your root and D as your destination. Okay, so let's go over the algorithm. So the first step is we're going to do the algorithm starting here. So the first step is you make all these initializations. So you realize that the distance from A to A is 0 because you're already there. The distance from A to B is infinity because there is no edge connecting A to B. So that's why this number is infinity. Okay, it doesn't want to. All right. And then to C is 47. To D is infinity because there's no edge from A to D. To E is 70, and so on. Right? So the ones that say infinity just means there's no edge that goes from A to that thing. So you initialize those distances, which are just, if there's an edge, it's the weight of that edge. If there's no edge, you put infinity. And then you create the path, like if you're going to C, it's just A to C. All right. And then you identify which one is the closest edge to A, which is F. Right? So if you look at these numbers and you exclude 0, the closest one is 24. So then you let, what is it called? You add F to sigma. Okay? So you realize this is the closest one. So now you're going to start looking from F. This is called the scanning from F. You started at A. F was the closest one. You moved to F. And now you reevaluate all your calculations. All right, so the distance to A is still 0 because, this distance is 0. The distance to B is still infinity because there's no path from F to, well, there's no straight edge from F to B. The distance to C is still 47 because 47 is smaller than 24 plus 25. The distance to D was infinity before, but now there is a path, 24 plus 120. So you get this 144 in the distance to D. And then the distance to E is still 70 because if you did 24 plus F to E, that's 24 plus infinity, that's bigger than 70. The distance to F is still 24 because you fixed that. And then to G you can't get there, to H you can't get there. So that's why you get those numbers here. Okay? So notice that because this was better, like if you just do A to B, the distance is infinity. So by putting in F in between, you get that value. So you update this path that way. So the algorithm is annoying because it's keeping a path for each one of the, like you want something to go from A to A, to go from A to B, from A to C, from A to D, from A to E, from A to F, from A to G, from A to H. So you're keeping track of a bunch of things. So a computer can easily do that, but it's annoying to do this by hand each step, right? You're changing a lot of things. All right, so that's step 2. Now you look at these numbers, and excluding 0 and 24, the smallest one is 47. I think. Yeah, so the smallest one is 47. So then when you're going to start step 3, you have the path A to F to C. Okay? So now you're going to scan from C. Alright, so the distance to A is still 0. To B, let's see what happens. So before it was infinity, but now we have the path 47 plus 55. So the distance is now 102. So that's why distance to B says 102. And it updates the path to be A, C, B. And then distance to E is still 70 because 47 plus 23 is also 70. So this one, because it's a tie, you just keep the one you had before. Although you have some freedom there. You could decide if you prefer this path to that, if you wanted to update it. But the easiest thing to program is you only change it if you beat what you already have, not if you tie it. Right? So then the distance to F is still 24. That's not going to change because it's a permanent vertex. And the distance to G, it was infinity before, but now you can do 47 plus 66. All right, so you get all these updates, and now if you look at the numbers here, and you exclude the vertices that are already permanent, so the permanent ones are A, F, and C. So if you exclude A, F, and C, the smallest number besides 0, 24, and 47 is 70. So that means you now start scanning from E. So now your permanent vertices are A, F, C, E. You start going outwards from E. The distance to A is going to be the same because it's permanent, to F is the same because it's permanent, C is permanent, E is permanent. So the only ones that could change are the other ones. So now we look at B. The value for B before was 47 plus 55, which is 112. 102. But now we realize that we could also do 70 plus 31. So you update that to be 101. Okay? And then the other one that gets updated is the distance to G, which used to be infinity, but now you can do 70 plus 42. So everything is updated. There's still no path to H, so that's still infinite. So now you look at which one's the smallest here, and the smallest seems to be 101. Yeah, because 101 is less than 112, 135 and infinity, so you make that permanent. And now you go to B, and you start scanning from B. And the distance to D, the best one you had before was, actually I don't know which one, maybe it was 47 plus 88. Or maybe it was 24 plus 120. So 47 plus 88 was the smallest one, but now you compare that to the distance from here to here plus 31, and the distance from here to here is 101 via this way, so you add 31, you get 132. So that one is updated to 132, and H, which used to be infinity, now you do have a path because you can get here and then there. So the number is no longer infinity, it gets updated. And now you look at which one is the smallest, and the smallest one is going to be 112. So now you make G permanent, you scan from G, the only one that changes is H, and You make that permanent, you scan from D, H changes again, you make it permanent, and now once every vertex is permanent, the algorithm ends. Okay? And so when you do this, when you finish with step 7, you get the distances from each, from A to anything. So from A to A is 0. From A to B is 101. From A to C is 47. From A to D is 132. From A to E is 70. From A to F is 24. From A to G is 112. From A to H is 161. And if you do the algorithm as described here, not only will you have the distances, it'll also, you can also keep track of what's the path that creates that distance. Okay? Now, there is like, if you're only interested in the distance, you can have a shortcut. So, like if you don't care about the paths, let's do the shortcut. I'll do it in yellow. So you start with A. So this is 0. This will be 24. This is 47. And that is 70. Those are the things that come out from A, right? And A doesn't touch anything else, so I'm just going to label the rest infinity. All right? And now, of these numbers, the smallest is 24. So now I set myself here, and I start going out from F. So I see from F to C, 24 plus 25 is 49. So 47 is smaller, so I keep the 47. 24 plus 120 is 144. It's smaller than infinity, so I change infinity. Well, I guess I'll mark it as I'm changing it, just so that we keep track of what's going on. And to B, there's no link, so it stays as infinity. To H, there's no link, so it stays at infinity. To G, there's no link, so it stays at infinity. And to E, there's no, it's still 70, right? Because there's no F to E. So after I'm at F, I recalculated things. The only thing that changed was this one. So I look at which one is the smallest, and the smallest is here, right? So now I'm here. All right? And now I start scanning from C. So from C to E, the value was 70. 47 plus 23 is also 70. So this value didn't change. 47 plus 55 is 102. 102 is smaller than infinity, so you change it. Here, 47 plus 66 is 113. That's less than infinity, so it changes. And, the other one I haven't taken into account is this line. So this is value 47, this is 88. 47 plus 88 is 135. 135 is less than 144, so I change it. Okay? And now I look at the values of the vertices that are not yellow. And which one's the smallest? The smallest is 70, right? So now I'm here. So now I just start looking at the edges coming out from E. So from E, I have these two edges. So 70 plus 31 is 101, which is smaller than 102. 70 plus 42 is 112, which is smaller than 113. And those are the only changes that happen because those are the only edges coming out of E. So now I look at the values left, and 101 is the smallest. And now I look at the edges coming out of B. We have this 31. 101 plus 31 is 132, which is smaller than 135. This is 79. 101 plus 79 is 180, which is smaller than infinity. 101 plus 74 is 175. That's bigger than 112, so this stays as 112. And now of the values left, 112 is the smallest, so I grab this. I look at the edges coming out of G. The only edge is 66. 112 plus 66 is less than 180. Now I compare these two numbers. This is the smallest. I look at the edges coming out of D. This is the only edge. 132 plus 29 is smaller than 178. And then the numbers I keep on the vertices are the answers. So the distances are 24, 47, 70, 132, 101, 112, and 161. You can see it, they're the same. So when you have to do this by hand in midterm 3, I think that would be a faster way to do it. You don't have to keep track of the paths, you just... So again, let me repeat how it goes. So you start, you look at the edges coming out of A, you put the numbers associated to them, so 24, 47, 70, and to everything else you put infinity. Then you look at the smallest one, that's F, and you look at the edges coming out of F. So from F to D, that's 120. So 120 plus 24, 144, less than infinity, so you replace it with 144. You look at this edge, 24 plus 25, it's not smaller than 47, so you keep the 47. There's no other edges, so everything else stays the same. Now this is the smallest. You look from here, 47 plus 23 is 70, that matches the number that was already there, so no change needs to be made. 47 plus 66 is 113, is less than infinity, so you replace it with 113. 47 plus 55 is 102, less than infinity, so replace infinity with 102. And 47 plus 88 is 135, which is smaller than 144, so this has to be replaced. So you just look at all the edges coming out of it, and you calculate, did the sum go down, yes or no? If it went down, you replace it. If it didn't go down, you keep it. And then you keep traveling. So that is Dijkstra's algorithm. And so if you wanted to know all the distances, then you kind of repeat this algorithm with different roots, right? So this particular directed graph has a natural flow of things, like things are going from left to right, basically. So if you start with H, H is a sink. There's no edges coming out of H, so if you start Dijkstra's algorithm with H, just this one will be 0 and everything else will be infinity. So, I mean, if you start with F, then this one is infinity. But I think you can reach all the others. So if something means infinity, it just means you can't reach it. If at the end of the Dijkstra's algorithm you get infinity, it means there's no path from here. Yep. Okay, so that is Dijkstra's algorithm. Now let's see why it's true. Okay, so we have a few propositions. So let X be a vertex. And you have a path that goes from so what I mean by this path is like over here if you have, let's see, so what was the shortest path to H? So to H, the shortest path was, so you started here and here and here. the path that's 180, I think. Alright, so the one that's 180 is that one. So 70, 31, 79. But we can beat it with 178. So that's because instead of going that path, we went from G to H. And how did we get to G in 112? We did AE. So 70, 42. So that was 178, but 161 was smaller. So we actually wanted to do, yeah, so we need A, E, B, E. So this is that's the path, that's the shortest path from A to H, this long one. So when I have this notation here, I just mean the path is A, E, B, D, H. So it's like in parentheses, and you start at U0, which is the root. There's a edge from U0 to U1, and then there's an edge from U1 to U2, and blah, 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 and there's an edge from UT minus 1 to UT, and then there's X. So suppose this is the shortest path. And so then, for every integer j between 0 and t, u0, u1, uj is the shortest path from R to uj. And uj plus 1 ut is the shortest path from uj to ut. So this is pretty easy to prove. If you had a shorter path from U0 to Uj, then just do that path, connect it with this, and you have a shorter path from U0 to X. Right? So suppose, for the sake of contradiction, suppose there is a shorter path from R to Uj. Okay, so if there is a shorter path, now consider E prime being that path. So let's call this R goes to B1, goes to B2, blah, 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 goes to BS, which is Uj. So now consider the path R goes to B1, B2, BS, which is Uj, and then you do Uj plus 1, blah, 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 UT, which is X. So this path connects from R to X, and the length of this path will be the length from R to Uj plus the length from Uj to X. But the length from R to Uj is smaller than this one. And this length is the same as over here. So the total sum is smaller than this path. But this path was the shortest path, so you get a contradiction. So it's pretty straightforward. Then the proof for the other path is the same. Okay, then we have another proposition. All right, so this one's pretty straightforward. The other one is a little trickier. So when Dijkstra's algorithm calls, then you have your permanent vertices. You have that these distances are in order. Okay, now why is that true? That's basically by construction. So if you think about it, I picked F to be the smallest one, right? And the first stage was F is the smallest. But now, because things are coming out from there, even after I make changes to the rest of the things, they will not be smaller than this. Now, so I guess I have to give you a caveat. Dijkstra's algorithm only works if the weights are non-negative. So if you decide to include things with negative numbers, this will not work. Okay? Now, in the real world, we like to include things with negative numbers. So it's kind of annoying that Dijkstra's algorithm only works for positive numbers. But there's a very easy fix. And the fix is, if you think about it, if I change all the weights by adding 10, what will happen to the distances? The distances will all just change by adding some constant, right? So the shortest path will not be changed because of this constant thing going on. So if you have negative numbers, you can just translate everything by adding a big enough thing so that there's no more negative numbers. I'm getting a little worried, and that might be false. Because if you have a path, yeah, that's false. So if you have a long path, right? It's like you added 10 4 times. So maybe you could have won by just adding 10 2 times. All right, well, Dijkstra's only works for non-negative numbers. I think this translating thing works, but it's actually not obvious because of this long path. So that it wouldn't be a required proof. But if everything is non-negative, then this follows. Okay? So if everything is non-negative, then when you scan out, nothing could have reduced a smaller next term in the sequence. So then we have these two propositions, and then what we're going to do next class is then show that once you have these two things together, you can show that this algorithm always gives you the smallest distances. All right. Have a nice weekend.